Alloy wheels are popular on cars. They're typically lighter for the same strength and they're shinier than normal steel wheels. Alloying metals greatly affects their properties, and to understand this we must first be familiar with the metallic bonding model. So with the metallic bonding model we have metal cations which form a regular lattice, and they're surrounded by a sea of delocalized electrons, which you can see in the yellow. And it looks something like this. Now if you're unsure about this model, please review my other video on structure and bonding. So alloys involve adding small amounts of other substances to metals, and this changes their properties of the original metal. And you can see here, this is a copper alloys, and this is what happens when you mix all of these different elements with copper. So if you want to increase strength, you'd add these elements. If you want to change the colour, you'd add these elements. Corrosion resistance, you'd add these, and so on. So there's two types of alloys. One is substitutional alloys, and the second one are interstitial alloys, and these are the two types that I want to talk about in this video. So substitutional alloys, it's exactly what it means, substitute. One of the cations is substituted by another metal. So some of the host metal atoms are replaced by other metal atoms, which are similar in two things. Firstly, size, so they've got a similar atomic radius, and also in bonding characteristics. What happens when you apply a force to a metal, a normal metal? What happens here is that the metal will reshape. Okay, it will bend, it's malleable. However, an alloy here, which you can see here, we've got a substitutional alloy, and this has been exaggerated just for the diagram, but metal ions have been replaced with something else, and you'll see when you add a force that the alloy will hold its shape, and this is because the metal ions here can't easily slide over each other, and this makes the metal both harder and less malleable. Brass is a typical substitutional alloy made up of copper plus 33.3% silver. And you think of brass, you think of things like bells, instruments, and those old-fashioned door knockers. Brass makes copper harder and less malleable, which suits it for these different purposes. Another well-known substitutional alloy are Australian silver coins. These are silver coins here. Now silver coins aren't made out of silver coins. They are a combination of 75% copper and 25% nickel, and you'll notice the nickel gives it the silver colour. And this also makes them harder and less malleable than pure copper. Aussie gold coins are also an alloy, and they're 92% copper plus 6% aluminium and 2% nickel. So the second type are interstitial alloys, and you'll see here straight away that these are in-between alloys. Interstitial meaning in between. So these are smaller particles that are put in between the regular lattice of the metals. So it's a small proportion of a significantly smaller element is added to a metal, as shown here. This makes layers again harder to slide past one another and makes the metal harder and less malleable. So here's a normal metal, and when we add a force, these metal cations easily slide past one another. However, when you add small numbers of another element, such as carbon, you form obstructions, and this makes it a lot harder when a force is applied on the side here for these cations to move past one another. So they form obstructions, which makes this sliding much more difficult, and thus you get a harder and less malleable metal. Interstitial alloys also have decreased electrical conductivity. When you have a look, you'll see that an interstitial alloy has obstructions here. The carbon or the interstitial component creates an obstruction to the electron flow. And so these obstructions here prevent the smooth flow of electrons through the metal and thus reduces electrical conductivity. Steel is one of the most well-known interstitial alloys. It's used for bridges, it's used for tools, and it's been around for ages. You can have different grades of steel depending on what you're wanting to use the steel for. Low-grade steel has a small proportion of carbon in it, and this makes it somewhat malleable. However, high-grade steel has a higher proportion of carbon in it. This makes it very hard, and it's tool-grade steel. But remember, a harder metal will also be more brittle and less malleable. Too much carbon, of course, would make the iron too brittle, and therefore you wouldn't be able to use it. Gold alloy. If you have a look at any gold jewellery, you'll see it's 9 carat or 14 carat or 18 carat. 9 carat and 18 carat are the most common in Australia. And especially in Asia, you'll find a lot of 24 carat gold. Now, 24 carat gold is 100% gold. But you'll find if you pick that up, you can actually press your thumbnail into it and make small indentations. Adding other components to it, such as listed in this table, will make it a much stronger, less malleable, less bendable piece of jewellery. Stainless steel is another interstitial alloy, and you see that all around us. It's often used to make tools. It's more popular than steel, and often used to make sinks. And the reason for this is that it's resistant to corrosion. Very resistant to corrosion. In other words, it doesn't rust. So it's iron with small amounts of nickel and chromium, and this has no carbon in it. Even though it's classed as steel, there's no carbon present. Solder is another interstitial alloy. It's an alloy of tin and lead, and it melts at a lower temperature than either of these two substances, or any metals in fact. And it's used to join metals together. You can see here you get a soldering iron. You only need a very low temperature to melt solder, but you're not then melting the two pieces of metal that you're joining together, and that's what makes it useful. You should be able to complete Chapter 5 questions now.